All right, in this video, we're going to get introduced to a method for approximating the value of a definite integral. And instead of using rectangles like we did in Riemann sums to approximate that area, we're going to use trapezoids. So let's get some terminology as far as trapezoids are concerned. And so in a trapezoid, you have two parallel sides. I'm going to call them B1 and B2. Those are the two parallel sides, or the bases. And then you have the height of the trapezoid, which in our case is sitting horizontally because it's the distance between the two parallel sides. We're also going to call this delta x since it's a distance along the x-axis. All right, let's take a look at our first trapezoid. So we're going to calculate the area of that first trapezoid. And the area of the first trapezoid is 1/2 times the base, times the height, which is 2, times the sum of the bases. And the sum of our bases is f of 1 plus f of 3. I'm not going to simplify that for the moment. The second trapezoid, which I'll highlight in a different color, is going to have the same height or horizontal distance of 2. So we're going to start out its area formula the same way, but its two bases are going to be f of 3 and f of 5. And then our third trapezoid area will be this one that I'm highlighting right now. And that trapezoid's area is calculated the same in the beginning because we have the same height, but our trapezoid bases are f of 5, the y value at 5, plus f of 7, the y value at 7. Now what happens if I add all these together? If I add them all together, I can factor out the 1/2 times the 2 and then just add together all of the f of 1s, f of 3s, f of 5s, and f of 7s. When I add them all together, I have 1 f of 1, 2 f of 3s, 2 f of 5s, and 1 f of 7. In general, when I'm using the trapezoidal rule or trapezoidal approximation for approximating the value of a definite integral, that area formula is going to be 1/2 times delta x times f of the leftmost endpoint for the interval plus 2 times f of the leftmost endpoint plus delta x plus 2 times f of the leftmost endpoint plus 2 delta x's plus, and then I'm going to use the ellipsis to indicate that there's maybe a bunch more terms, plus 2 times f of b minus delta x would be the second to last term, and then the very last term would be f of b, which is the rightmost endpoint of our interval. One of the things that I want to point out about the trapezoidal rule that's going to be different from Riemann sums is we have 3 trapezoids, but we have 4 y values to consider here. So we use both the left and the right endpoints. A quick note about this, the trapezoidal approximation is actually just the average of the left and the right endpoint Riemann sums. So it's kind of like getting a happy medium between those two estimates. The shortcut that we wrote there is actually only valid if delta x is the same for each subinterval, so if the subintervals have equal widths. Now let's talk about overestimate, underestimate. What you will notice about the 3 trapezoids that we drew above is that those 3 trapezoids are doing a much better job than rectangles at estimating the area, but they're still just a little bit under what the actual value of the integral is because we can see these empty spaces here. Let me point those empty spaces out to you. The empty spaces are that little portion, and that little portion of the graph. And so this particular integral we're underestimating, and the reason that we're underestimating is because the graph of f of x is concave down. If it's concave down, those trapezoids will be not quite give you the entire area. And you guessed it, if f of x is concave up, then we're going to see an overestimate. So our trapezoids will actually be a little bit above the curve. All right, let's do a trapezoidal approximation for a particular integral, and this is an integral that we have no idea how to actually do because we don't know the antiderivative of 2 to the x over 3 just yet. We will eventually know that one. So what we've got are 4 equal subintervals, and we can calculate what our delta x is going to be. Our delta x is the width of each subinterval, and that subinterval width can be found using b minus a over the number of subintervals. So that's going to be 9 plus 3 is 12 over 4 gives us a delta x of 3. So that's important to know. And you don't actually have to show that calculation. You can just kind of look at that interval and say from -3 to 9 is 12 units long. And so dividing that into 4 equal subintervals, each subinterval will be 3 units long. And so what we're going to do next is our approximation is 1/2 times our delta x value times f of -3, our leftmost endpoint, plus 2 times f of, and we'll move over delta x. Moving over delta x will bring us to 0, 3 units to the right of -3. Plus 2 times f of, move over 1 more delta x to 3, and then plus 2 times f of 6 plus f of 9. Our rightmost endpoint gets a coefficient of 1. So looks like we have 3/2 times, and our f of x is just the integrand function. By integrand function, I mean the thing that we are trying to take the integral of. So our f of x is 2 to the x over 3. So if I plug in -3, I'm going to get 2 raised to the -1 power. And then if I plug in 0, I'm going to get 2 raised to the 0 power. Plugging in 3, we get 2 raised to the 1 power. Plugging in 6, we get 2 squared. And plugging in 9, we get 2 raised to the 3rd power. All right, so I have 3/2 times 1/2 plus, and that's going to be 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8, and 2 cubed is 8. And so that gives us 3/2 times, and what do we have here? 16, 20, 22, 22.5, which is 45/2, and that's going to give us 135/4 is our trapezoidal approximation. So this means that the integral from -3 to 9 of 2 to the x over 3 is approximately equal to 135/4. Okay, let's check out another example. In this example, we have a trapezoidal approximation that's given to us, and we're going to work backwards from it to try to find the actual definite integral that fits that description. So what I want for you to notice is that each of these right here are our function values. You'll notice the 1, that's the coefficient of the first term, and the 2, that's the coefficient of the second term, 2 that's the coefficient of the next term, etc. So this is actually our f of a, where we're talking about an integral from a to b. And this last term right here is actually our f of b. What you'll also notice about this is that the x values move by 0.05. So our delta x is 0.05. So we know a couple things already. What else do we notice? You might also notice that if a is equal to 1, a is equal to 0, that's our leftmost endpoint, and b is equal to 1, that f of x must be x cubed. Let's also just take a look at that 1/40th at the beginning. You might remember that the trapezoidal approximation starts with 1/2 times delta x. And so 1/2 times delta x is 1/40th. Multiplying both sides by 2, delta x is equal to 2/40ths, or 1/20th, which happens to be 0.05. So things are working out consistently. We can verify several of those things. So the integral that this represents is actually just the integral from a, which is 0, to b, which is 1, of the function x cubed. And that's all we had to do. Now, just a quick note, this is not the only integral that this trapezoidal approximation could represent, but it's probably the easiest one to come up with. And next, we're asked to evaluate that integral. So evaluating the integral from 0 to 1 of x cubed is equal to x to the 4th over 4, evaluated from 0 to 1, which is 1 to the 4th over 4 minus 0 to the 4th over 4, which is just 1/4. Next thing we're asked to do is just to determine whether that trapezoidal approximation estimate is actually greater or less than the integral. So which one of these two things is bigger? So what we do know is that our integral is representing the area under the curve, or between the curve and the x-axis, from 0 to 1 of y equals x cubed. So you'll notice that y equals x cubed is a curve and therefore has some concavity to it. So let's determine what the concavity actually is. So y prime is 3x squared and y double prime is 6x. Y double prime tells us about the concavity, and y double prime is positive when x is positive and negative when x is negative. And so the function y is concave up, which we can kind of see from the graph anyway. We knew what the graph of y equals x cubed looks like, and on the right side, the graph of x cubed is concave up. And so what does that mean? If we try to fit it with trapezoids, the trapezoids are going to overestimate the area. Our trapezoid, if we just did a single trapezoid, would actually be a triangle there. And so if the trapezoidal estimate is above the curve, then our trapezoidal estimate is bigger. And that's it.